Earlier in this lecture, I talked about how modern cloud-native applications are becoming more event-driven from an architectural perspective. And I want to talk about a couple services that are available within AWS that help support this sort of event-driven, message-driven architecture. The first service is the Simple Notification Service, or commonly known as SNS. SNS is a service that allows you to publish messages from an application and deliver those messages to subscribers. And subscribers could be people, they could be devices, they could be other application services. When you publish a message in the SNS service, SNS can send that message to a subscriber using email, it can send text messages using SMS, it can send a mobile push message to something like an iOS or Android device. It can send them to a message bus, a message queue called SES or SQS, which we'll talk about in a little bit. It can even send messages to websites via an HTTP endpoint address. The way SNS works is that you define a topic, and a topic is essentially like an access point that you can publish messages to. When you publish messages to a topic, then the topic the message can be delivered to the people that subscribe to a topic. And you can subscribe to a topic using a variety of different methods, as I mentioned, email or text or an HTTP endpoint or a mobile push. The messages that are published to the SNS topic are going to be stored in multiple availability zones within that particular region. And that gives you redundancy, right? If you lose an AZ, then your message isn't going to be lost. And you want this sort of message bus to be extremely resilient because generally these messages contain very important information. As I said earlier, you have the producer who is producing messages and publishing them to a topic, and then you'll have these recipients, these consumers of messages. The recipients will subscribe to the topic and specify that they want to receive messages that are published to the topic. So the way this essentially works is that messages are being pushed to recipients, and they're being pushed to the recipients that subscribe to a particular topic. Why would you want to use a service like SNS? Well, you would use it because you want to send out event notifications. You might have a service that wants to notify another service, and it would do that by publishing an event. You might want to notify your staff members in your company via email if a certain CloudWatch alarm is triggered. You could use SNS to alert people via email or even via a mobile text message. So anytime you want to send out an alert or publish an event or message, you could do that using SNS. SNS enables a particular application development pattern called the publisher subscriber pattern, or also commonly known as PubSub. This is where we have an application which needs to, or a service which needs to notify other applications or services about particular activities that are happening in the platform, that the service can publish an event. And then you have this sort of message broker, which in this case is the SNS service, which is then allowing subscribers, other applications and services, to receive that message because they are subscribing to a particular topic. And what this allows for is loose coupling of these services. The publisher of the message doesn't need to know anything about the subscriber of the messages, and vice versa. So the two services don't need to know anything about one another. The publisher just needs to know the topic that it's publishing messages to, and the subscribers just need to subscribe to the same topic in order to receive those messages. The second service that I want to talk about is a service that, again, enables an event-driven sort of architecture. And this is the Simple Queue service, or the SQS service. The Simple Queue service enables the message bus pattern that I talked about in the first lecture of this course. It allows messages that are generated by one component, system component, to be consumed by another component in the system. And interestingly, this was the very first service that was launched by AWS back in 2005. And message queues are just a critical component of a cloud-native application platform. And a company like Amazon and their Amazon.com platform likely has thousands and thousands of these queues in place. The Amazon SQS service allows us to support asynchronous communications between message producers and message consumers. In this case, you might have cases where you have you have a service that's calling another service, and the second service may be busy. It's processing requests that are coming in from other services, and so in order to prevent the second service from being overwhelmed by requests, we can queue those requests, or we can buffer those requests for a period of time, and we can buffer the requests in an SQS queue. So why would you want to use SQS in the real world? Well, you could use it for a variety of different workflows. For example, maybe you have a customer that uploads their image to your website. Maybe you allow the customer to create an image associated with their account profile. And when that image is uploaded, it fires off an event which is placed in an SQS queue. And that event could be initiating a workflow to generate a thumbnail image based on the image that the user uploaded into an S3 bucket. You might have a payment process workflow that's initiated if orders are placed on your website. Maybe you just have certain services in your application which are very bursty and may be overwhelmed by requests. And so in order to regulate the flow of requests in your platform between the producers and consuming services, you might introduce an SQS message bus, this buffer, to regulate the requests within the platform. Now, the SQS message queue stores messages, and these messages can be up to 256 kilobytes in size. So, when you think of a message, think of like a text object that contains some data. The messages that are stored in the queue can be stored there up to 14 days. Now, but the default is 4 days, but you can raise that up until 2 weeks. After 2 weeks, then the messages, if they haven't been consumed yet, are simply going to be discarded. Now, there are two different types of SQS queues that you can create in AWS. The default type is what we call the standard queue. And in the standard queue, the messages are guaranteed to be delivered at least once, but possibly more than once. And we'll see why here shortly. But this is an important point. That when the publisher publishes a message into the SQS queue, it's the SQS is guaranteeing that that message will be delivered to consumer at least once, but it's possible that the message might be delivered more than once. And the messages that are delivered might be occasionally delivered out of order. So the ordering of the messages is not guaranteed. In other words, you've got producers who are pushing messages into the SQS queue. Those messages might not necessarily be delivered to consumers in the same order that they were pushed into the queue. So because messages might be delivered more than once, we want to ensure that any actions that are taken on these messages are idempotent, which means that if a message is processed more than one time, in other words, messages processed 2 or 3 or 4 times, the fact that the message is processed multiple times won't actually change whatever the ultimate result is of that action. So, we wouldn't want to use the sort of SQS queue if we were processing ATM transactions. That could be bad because you might have an ATM transaction to debit or, take out $10 from your account. And the message is saying, remove $10 from your account. Well, if that message is processed multiple times, then you'd have more than $10 taken out of your account. You could have $20, $30, $40 removed. That sort of transaction is not idempotent. SQS, the cool thing about SQS is that it scales to really, really high levels. You can process like thousands, tens of thousands of transactions per second. So this is designed to scale up to, to support really, really, highly scalable platforms. The second type of queue that you can create is the FIFO queue, which is the first in, first out queue. And this queue will deliver messages only once, so exactly once. There's no possibility of a message being delivered more than once. And messages are going to be delivered in a strict order. They're going to be delivered in the same order in which they were pushed into the queue. You can create multiple message groups within a particular queue, which allows you to set up different types of consumers as well. Now, the big limitation with FIFO, everything sounds great, right? Messages are only delivered once. Messages are delivered in a particular order. That sounds great. But the price you pay for this first in, first out guarantee is that you are limited to 300 transactions per second, which might be perfectly acceptable for many types of platforms. But if you need to scale beyond that, then you'll have to live with the differences and limitations of the standard queue. So how does SQS actually work? Well, this set of diagrams kind of shows us the sort of sequence of activities that are taking place in an SQS queue. At the very top, in sort of step 1, we have some sort of service which is going to send or push a message into the SQS queue. And when the service pushes a message into the queue, what will happen is that a visibility timeout clock will be set for that particular message. And the visibility timeout clock, in this case, we're saying it's 40 seconds. So the message is sitting in the queue. It has this visibility timeout clock associated with it. In the second step, we have another component, another service in our application, which is going to retrieve that message from the SQS queue. And as soon as that second service retrieves the message, the visibility timeout clock starts ticking. It's like a timer. And as long as that visibility timeout clock hasn't reached 40 seconds, then the message will no longer appear in the SQS queue. So it will appear as if the service has removed it from the queue. Technically, it's still there, but it's just not visible. No other services can retrieve that message while the visibility timeout clock is running. So in the third step, the service which had retrieved the message will process the message. And when it's done processing the message, it will delete the message from the queue. And again, it has to do that before this visibility timeout clock reaches 40 seconds. So what happens if a service has retrieved a message and the visibility timeout clock is running, so no other service can see the message on the queue. No other service can retrieve that message. The service has retrieved the message and it's attempting to process it, but the visibility timeout clock reaches 40 seconds before the service is done processing it. Well, at that point, then, the message becomes visible again on the queue. And it's possible that some other service will retrieve that same message. And now you have sort of two services out there that have both retrieved the same message and are processing it. So that's what we mean by, there's a possibility with this is where we're talking about the standard SQS queue in this diagram. There's a possibility that a message will be delivered to another service more than one time. And it's because of the possibility of this visibility timeout clock running out and a message reappearing on the queue again. Well, why use it? What is the purpose of this visibility timeout clock? I mean, why do we even bother with this in the first place? Well, this is to ensure reliability. This is to ensure that a message is going to be processed on the queue. I mean, imagine a situation where you had a service which retrieves a message from a queue, begins to process it, and then the service fails. Well, if you didn't have some sort of visibility timeout clock, then that message that was retrieved by the failed service would never, ever get processed. And that's highly undesirable, right? We want every message to get processed at least one time. And so the visibility timeout clock ensures that any messages which failed to get processed properly are going to end up back on the queue and can be retrieved by some other service which is healthy. The price you pay for that is that the actions taken on these messages when they're processed has to be idempotent. This SQS queue in the example, the visibility timeout in the SQS queue was 40 seconds, but we can actually set that visibility timeout up to 12 hours. And the question is, well, what should it be set at? Well, that's going to completely depend on the application that you are building. So this is a value that you'll have to tune and set appropriately for your particular use case. Now, one of the challenges that you can potentially run into is that you have these sort of consuming services that are pulling messages from the SQS queue, and they're having to kind of constantly pull the SQS queue to see if there are any new messages available in the queue. And this polling mechanism can really add up. I mean, like if you have a service that is polling the message queue for new messages every 5 seconds, then that single service is going to make over 500,000 requests to SQS every single month. If you just have 4 services that are polling messages, that means that over 2 million requests a month are going to be made to the SQS service looking for new messages, which is really wasteful because, you might not have new messages entering the queue all the time. The services are just polling the queue and there's no messages there. There's nothing for them to do. So in order to sort of mitigate the frequency of message polling, you can enable a feature called long polling. So instead of having to poll the queue, every few seconds to see if messages are available, the consuming service can poll the queue and keep that polling request open for up to 20 seconds. And if any new messages arrive in the queue during that long poll, those messages are going to be streamed to the consuming service. SQS allows us to support an architectural pattern called the competing consumers pattern. This is a pattern where you might have multiple applications or multiple services attempting to read messages from the same message queue. So on the left-hand side, you have an application, maybe multiple services in an application that are all publishing messages to a message queue. And on the right-hand side, you have consuming services, and it could be multiple consuming services, which are all trying to retrieve and process messages that are ending up on the messaging queue. One thing to note is that you cannot set a priority level for messages within the SQS queue. Every message that you push into the queue essentially is treated the same. And there might be cases where you want to have sort of different message queues that have different priorities associated with them. You might have different sorts of events that have should be given a higher priority than other events. SQS doesn't natively understand any sort of prioritization of events. And so in order to support this sort of use case, what you essentially need to do is just simply create multiple SQS queues. You would have one queue that you would define as your priority queue, and then you would have a second queue which you would consider to be sort of your default or secondary queue. Another architectural pattern which is really common is to leverage an SQS Fanout pattern. And this is a pattern that actually combines both SNS and SQS. And the idea is this: you might have some sort of an event which will trigger sort of multiple processing steps. And you want those processing steps to happen in parallel. Well, in order to do that, then you essentially need to take one message and turn it into 3 different messages, for example. And in this case, we have a customer that is uploading an image to our platform, and that image upload is going to trigger a notification. The notification is going to be sent out by SNS. And SNS will send out a notification to a topic. That topic is going to be subscribed to by 3 different SQS queues. So the SQS queues are acting as consumers that are subscribing to this SNS topic. And when that message comes in, then that will trigger each SQS queue. The first queue is going to generate a thumbnail. The second queue is going to do some image recognition. In this case, it'll recognize that the image is a baby. And the third queue is going to perform some processing on the image metadata. So this is an example of how you can combine SNS and SQS to actually create this sort of fan-out pattern and parallelize some of the steps associated with processing a particular message.